So, this test application process for the interconnect testing, the problem that we have is that we for individual links. So, we are having this test data generator and this test error detector TDG and TED, which is lot of overhead, in the sense that all of the, so as I have said that they are normally having some finite state machine implemented there. So, the overhead may become large if there is a large NOC with a large number of links. So, other possibility that we have is to have some global test controller. So, this global test controller, so it can generate some it will have this TDG test data generator. So, this TDG, so this is generated on by at one TDG, and it is it will be transferred to all the links. So, MAF test patterns, the multiple aggressor fault model test patterns, maximal aggressor fault model test patterns, they are broadcast to all interconnects by test packets with only one TDG. So, I have got only one TDG here. So, it will be broadcasted to all of them, and there is a global test controller. So, which will be controlling this broadcasting process. So, here see the first this from TDG. So, it is connected to this, it will get connected to this TED. So, as a result it will be coming to this test this interconnect, and this TED will do the analysis, and it will send the information back to the global test controller about the status of this one, and then it can also this will also get forwarded to the next link. So, that way the next link can be tested, and that will be giving the information back to the global test controller. So, only one set of interconnect between a pair of routers can be tested for each test pattern that is broadcast, because this will test this one. After that, so it will be assumed that this is okay, now it will test this one. So, that way one set of interconnects can be tested, and a global test controller and many these TEDs, so test error detectors. So, they are required. So, that is the situation of applying this unicast method. Under a multicast mechanism, so these test packets are broadcast to interconnects of different pairs of routers to achieve maximum parallelism. So, here what is done from this test data generator. So, this is broadcast to this link and this link. So, both of them are being tested simultaneously, and then this TED, so error detector. So, they detect the response, and they, if they find some error, so they will tell the global test controller that some error has been detected. Similarly, then since it is a broadcast mode, once this link is correct, so this router will get the test pattern, and it will send this test pattern to the next link. Okay. So, that way it will be going to the next link. So, that part will be tested, and similarly so these links will also be tested. So, this link will be tested in a broadcast fashion, this link will be tested. So, this way very fast, so all the links will get the test patterns, they will get tested. The TEDs will store the status about their correctness and all the, and the TEDs will transport those information back to the global test controller. So, test packets are broadcast to interconnects of different pairs of routers to achieve maximum parallelism. Multicast is a good compromise between test application time and hardware overhead, because multicast is going to help in this reducing this test application, transporting the test application pattern, the test patterns to the interconnects. Point to point or unicast test method has the smallest test point to point that will have the that has got the smallest test application time, but the largest hardware overhead, because in point to point case. So, we have got this dedicated test data generator and test error detectors. So, those modules are there. Now, they are so there the testing is the fastest, but the hardware overhead will be maximum, because so many TDGs and TEDs are required. On the other hand, we have got this multicast based approach. So, that is going to have faster test time, and the overhead is also reasonably low. And the other option that we have seen, the unicast method. So, it has got the largest test application time, but the hardware overhead is smallest, because individual routers, they need not have the broadcast facility. So, as I have said already, that this testing can use the broadcast mechanism only when we have got this part taken care of, that is this broadcast facility is available with the router. If it is not, we cannot do this thing. So, apart from testing the interconnect, so we have talked about testing of cores, testing of interconnects. Now, what remains is the testing of routers. So, routers are used to implement functions of flow control, routing, switching, buffering of packets, etc. So, it has got a good amount of logic in it, and there are different types of structures, like see this is a, if this is a system on chip. So, we have got these individual cores, they are connected to the routers. So, these cores are connected to the routers, and there is an interface which is basically the network interface NI that we have, that is there. So, through which these cores are connected to the routers, and we have got this channel. So, these lines are these links are the channels, and this is also the channel. So, the channel we have seen how to test the channels, but by means of that interconnect testing. We have seen how to test this cores, because core test patterns are provided by the vendors, and by test scheduling approach. So, we could apply those test patterns to the cores for testing. What remains to be seen is how to test these routers, and router testing is difficult, because router testing can be treated as a sequential circuit testing by taking its property of regularity. So, what happens is that all these routers, they are similar in their structure. So, that is one good thing, but at the same time these routers have got within them some sequential element as well as some combinational element, and as soon as we have got sequential element and there we have got discrete flip flops, as well as we will have some memory components there. So, memory testing we will see that is another very challenging task to be done, and this those memory testing part also has to be a part of this router testing. Okay. So, since the routers are all similar in nature, so it is desirable that we do a test pattern broadcast. So, by doing a broadcast, so we can so the same test pattern set can be sent to all the routers for testing. The routers can do a self test and come up, there may be some error detector which will be determining maybe based on some signature register or something like that. It will combine the responses and see finally come up with the answer whether the router is working correctly or not. So, that way we can have this, if the broadcasting features are available, then we can use it for this testing purpose of the router. So, before going into this router testing part, so we need to understand how does a router look like. Okay. So, you see a typical switch or a router, it has got a number of ports. Okay. So, it has got primary inputs, it has got this input ports coming from different neighbors. So, it is in this case it is assumed that there are three input port, global input port, and one local port. So, this router that is discussed here, so it has got 3 ports. So, this router, so there is a local port here. So, this side I will connect one core. Okay. So, this is one port, and there are 3 other ports to which these the neighbors will be connected. So, another router will be connected here, another router will be connected here, another router will be connected here. So, when I am talking about say this router, then what is the structure of it? So, it has got for every site. So, every site, so this is a bidirectional link. So, I can break it up into 2 links, one is coming to the router and one is going out of the router. So, a traffic which is coming from this port, so it may be required to be directed to this port, or it may be required to be directed to that port, or it may be to the local port. So, there has to be a decision module which will decide which will look into the destination address of the packet that has arrived, and accordingly take a decision to which port this incoming packet should be put into. So, we have got a number of input ports. So, every channel that we have, or every input, primary input that we have, it goes into one input port, or we call it IP. Okay. Now, input port it contains buffers, okay, because the path may not be immediately available, so that it can be switched to the destination port. So, there is a buffer of, in this particular example, there is a buffer of depth 4 in each of the input channels. So, if the buffer depth is large, then it is good, because we can buffer maybe the entire packet into the into this buffer, but that will increase the complexity of individual routers, and as we have said that the individual routers are going to be very simple. So, this buffer depth cannot be large. So, normally it is kept as 4 to 6, not more than that, and as a result a packet gets distributed over fleets, and each fleet, some of the fleets of a packet will be available at a buffer of a router. Now, out of these fleets there is one header fleet which identifies the destination address, source address and all that. So, that destination address has to be analyzed, and it has to find out like what is the routing to be done. So, there is a module which is called routing and arbitration module. So, this will decide, like it will look into the header fleet, and it will decide how this packet has to be transferred to the output port. So, which output port it should go depending upon the destination address. So, this routing function will run, and it will find out the destination port. So, it may be XY routing, it may be some other routing policy, but whatever it is, ultimately it identifies the output port to which the packet will go. Now, also there is arbitration, like if there are say multiple packets which are asking for same port, then I have to tell like which port will which packet will go first, and the other will be waiting. Similarly, there may be through this switch at one point of time only one packet will go. So, we have to see like which one will be picked up. Maybe we follow a round robin policy. So, one of the packets are picked up, one of the packet is given green signal to proceed through this switch, and this switch part. So, this is actually some sort of crossbar type of connection, where from each of these input ports, that is the local input port and the 3 neighboring routers input port. So, they will be routed, and they will be connected to one of these output ports. So, this is the arbitration, the arbitration part that is done. So, the switching part will be this routing and arbitration module. So, it controls the switch. So, the switch is configured like this. So, you can understand that this FIFO, the first in first out buffer that we have, so that definitely has got the memory elements in it. So, the testing of this part should be done using the memory testing policies. Similarly, we have got this switching part. So, the switch part is designed, it is a crossbar. So, it is a combinational logic. So, this should be a combinational testing, and this routing arbitration part. So, this requires some sequential element and some combinational element. Like if we are going to do say round robin arbitration, then we have to remember like which module, which channel got chance last time. So, we need some amount of memory. So, the sequential elements will be needed. So, this way we have got this sequential and combinational elements in the routing arbitration module, and we have got this switch part which is combinational, and we have got this memory part in the FIFO. So, that way this testing of this router is a heterogeneous task. Okay. So, it is not very simple. Only thing is that the router itself being very simple. So, maybe the magnitude of the problems may not be that much severe. So, this is the thing, that this testing of a router, testing a router consists of testing the control logic, routing, arbitration and flow control modules, and the first in first out buffer. So, flow control module is basically what happens is, whenever this FIFO some locations are free, then only from the previous router some part of the packet, some of the fleets may be brought into. So, that is controlling the, that is doing the flow control. Otherwise, there will it may lose some of the fleets. The flow control has to be, the flow control module is not shown here explicitly, but that has to be there. So, this control logic has to do this thing, and the FIFO buffer. So, all of them are to be tested. So, control logic can be tested by typical sequential circuit testing methods such as scan testing. So, this routing arbitration and control logic. So, as I have said that they have got sequential elements in them. So, they can be tested using some scan type of philosophy. So, all those flip flops is put into a scan chain and then they are tested, they put into the input patterns can be applied to that. And for the FIFO part, so it may be better, it may be a smart way to test the FIFO is to configure the first register of FIFO as scan register. So, this FIFO has got 4 registers. So, first one is configured as a scan register, so that we can put any desired pattern into this, and then the others are can be tested by the scan register. Now, this since it is a FIFO, so there is a facility provided in this module, so that the content of the first location can be shifted to the second one, to the third one, to the fourth one. So, if you load a particular scan pattern here and then transfer it by shifting to the lower cells, lower FIFO cells, then that way all the FIFO locations can be tested. So, this is the FIFO operation that. So, this is the overall crux of the router testing. So, since all routers are identical, all can be tested in parallel by test pattern broadcasting. So, this is the thing that I have already said, that we can say that okay, whichever test pattern, so same test pattern is sent to all of them. So, from the from the scan input, so we can send the test patterns to all the routers, and assuming that we have got the scan chains for configuring for the control logic, and the FIFO part is also configured as the first location of FIFO configured as a scan chain. So, through that scan chain, so we can send in the test patterns, and then it will do after the test pattern has been sent in a broadcast mode. So, it is going to all the routers, then they will do their own testing, and once the testing is done, then the response will be coming, and it is put on to an equality checker. This equality checker, it will be holding the correct responses for all the test patterns that are applied, and it will do a equality check. So, there is a select function. So, there are 4 routers here 0, 1, 2, 3. The select function will select the input from here, and then it will do the comparison. Accordingly, it will tell the scan out line whether the particular router was okay or not. So, comparator is simply XOR gates, and naturally it can also do some sort of diagnosis, because now this comparator it will know, like if there is a mismatch, it will know for which router there is a mismatch, and it will try to see like for which pattern it has failed and all that. So, there may be intelligence clapped onto this, and what happens is that in case of NOC design, so we always keep some spares. Okay. So, if some router is determined to be faulty, so we can take help of some other router, and the core that is that was attached to the previous router is transferred to to another good router. Okay. So, the core that is at the faulty router gets transferred to a functionally correct router. So, this way we can take. So, there are many works on this fault diagnosis and the fault tolerant NOC designs and all that. So, they actually rely on this type of principle. So, for the router we have to design the test wrapper. So, again the same thing, that is IEEE 1500 compliant wrapper is designed to support this test pattern broadcasting and test response evaluation. So, you see that in the test wrapper is designed like this. So, we have got the functional inputs, we have got these special inputs for these control ports, and this these scan inputs. So, this is the scan inputs, they are feeding this scan chain 1 and scan chain 0. Then this scan chain serial input 0 is feeding this functional inputs for the functional ports of the routers. So, they are all those routers are all those functional ports, they are put on a chain. So, they are being fed by this scan input 0, and then scan input 1 is feeding this scan chain 0 of all the routers, and scan input 2 is feeding the scan chain 1 of all the routers. So, this way all the routers are fed with the test patterns required for a particular test pattern can be loaded to all the routers. So, they do the operation, and then the equality checkers are there. So, equality checker for this scan chain output. So, this scan chain output and the correct one. So, that will be there. So, that is evaluated. So, scan select, so that is a select function out of this R routers, it will be out of n routers that I have. So, it will be selecting some of the router, it will be selecting one router and do the comparison check, and after that comparison, so we have got so many comparison checks. Okay. So, the comparator module, so their results are available at this point, and through the these scan out lines. So, this they will be available on the scan out lines. Similarly, this functional output lines, so they will also be available on this scan chain. So, the 3 scan chains are there. So, SI lines, they will be giving the test patterns, and this SO lines, they will be giving the responses. So, we can have a diagnosis control block. So, that is optional. So, this is actually trying to see if some router has failed. So, if some router has failed, then it can initiate some fault tolerance mechanism, by which it can just see like what sort of pattern, what sort of for which router has gone faulty, and accordingly it can try to see, like it can try to which router has gone faulty, and it can arrange for a replacement of it. Now, some extra things that are needed is this part and this part. So, you see all the routers are put onto this test wrapper. So, that is a big challenge, putting all the routers onto this thing. So, you see that entire NOC is getting wrapped by a wrapper like this. So, that is the modification that is there. So, it is for SOC testing. So, this was not required, but for NOC testing, so if we are going to test all the routers together, so we have to have designed this type of router wrappers. So, this is the like all SC1 chains of these routers share same set of test patterns. So, D in 0 data inputs of all these routers share same test pattern. So, that we have already seen. So, diagnosis control block can activate diagnosis, small hardware overhead about 8.5%, and small number of test patterns, some hundreds due to test broadcasting. So, this will be required. So, overhead reduces significantly compared to the overall chip. Small test application time using multiple balanced scan chain and test broadcasting. So, that can also be done. So, the method becomes scalable. So, with the increasing number of routers in the NOC, it is not that this time requirement or the hardware requirement increases exponentially. So, coming to the concluding remarks. So, state of the art techniques for SOC testing we have seen. So, we have seen the modular test techniques for digital, so they can be developed. So, these modular techniques can be developed so that they can be integrated with this SOC testing mechanism. Test data bandwidth needs for analog codes are very different from digital codes, and unified top level testing of mixed signals SOCs. So, that remains a major challenge. So, this as I said, the analog testing is a challenge. So, that continues here also. Research is needed to develop wrapper design techniques and test planning methods for multi-frequency code testing. So, these wrappers are not capable of handling multiple frequencies. So, maybe something can be done there. RF interconnect technologies are coming up. So, they can also be, and when the interconnects are operating in the gigahertz range, then this RF will come into picture. So, they will be they are to be taken care of. Advances in testing of NOC based systems we have seen. So, how to utilize the on chip network as a TAM without compromising fault coverage or test time. So, that is the thing that we are going to, that we have addressed in the NOC testing. So, NOC testing research is still premature, and naturally, so in fact, NOC itself is going to come up, and then it is in the future it will be developed, and these research methodologies are going to be developed, which will solve this NOC testing problem significantly. Wrapper design techniques for SOC testing can be adopted for NOC based systems, and we have seen, but we have also seen that this 1500 wrapper needs to be modified for NOC testing. So, that is to be there.